Okay, cool. Let's begin. Good morning. Last day of Oracle World and Code 1. This session today is about productionizing machine learning in hybrid architectures, and I will show what role Apache Kafka can play here at many of the projects we see in our customers. My name is Kai Wehner from Confluent, and I really talk to customers around the world, around 100, 150 a year. So I see a lot of these architectures and different use cases and challenges. And that's in the end what I want to show today a little bit more so that you can learn from these experiences. So this is my third talk here. I had another one already about machine learning with Python, Kafka, and Jupyter and so on. So that was dedicated more from the data scientist perspective. This one here is now more general to really talk about a story, end-to-end deployment from machine learning with Kafka. And therefore, what I want to show today is in the end a use case. So this is a fictional story, but in the end it's really exactly more or less what many of our customers also do in a similar way. And what I choose here is the automotive industry, because that's a very interesting challenge and use case, because here it's really big data and large scale, so it's even more challenging to deploy machine learning to production compared to very simple and lightweight use cases. So the idea is really the classical thing about digital information, and the automotive company has to find new revenue models and all these things. But the point here really is, from the perspective of this talk here, we already have the connected car infrastructure in place. So that's already what also many customers in the real world have today already. So for example, Audi in Germany, they have already built this running in Germany really at scale for connecting to the cars in real time, and they are now spreading this out over the world. So this is meant to be existing here for this scenario, because what we want to do and show how you can leverage machine learning together with Kafka to deploy and train models at scale in a reliable way, to even add more business value or any other advantages with that. One point I want to make in the beginning, with machine learning, I don't mean just the really fancy stuff. With connected cars, you often think about autonomous driving, right? So that's typically still a few years until that will go to production everywhere on the planet. Here it's really more also about the more traditional use cases, which exist already, but still you can improve them with machine learning. And that's exactly the point, because even a car manufacturer has use cases already, like predictive maintenance or like transportation rerouting, like you see here as examples. But now with machine learning, you can make that much more powerful to reduce cost or increase the customer value or these kind of things. To have the same understanding of what I mean with machine learning, here's just one slide to define what I mean with that. So with machine learning, I mean that it allows computers to find hidden insights without being explicitly programmed where to look. That really means that you ingest the data into a data store, and then you have historical data, and the algorithms can take a look at that to find insights, depending on the use case, like fraud detection, predictive maintenance, cross-selling, or whatever you want to improve with machine learning. And therefore, under the hood, it's really not magic, it's really algorithms. So that's pretty simple things like decision trees or clustering, or then the more powerful but also more compute-intensive stuff like deep learning with neural networks. So for example, you can use convolutional neural networks for image recognition, or what we will see later in our live demo is an autoencoder which does anomaly detection. And we will deploy that in real time. That's the demo today in the end of the session, so that we can really do things like predictive maintenance in real time and alert the driver to stop the car before the engine is braking. So with that, let's think about how such a customer or project can realize this kind of use case of predictive maintenance for anomaly detection in real time. And in general, the first thing you do typically is you go to a data scientist and say, well, we have some historical data from sensors from the cars, and please train a model so that we can do predictive maintenance with that. And typically the data scientist uses Python, right? Some use R or maybe Java, but 95% or more use Python for that. That's the language for data science and machine learning. And that's also where all the frameworks are built for. In the example today, I talk mostly about TensorFlow, but in general, it doesn't matter which framework you use here. It's more about the algorithms under the hood. And the big problem here is that on the one side, when you go to the TensorFlow website or any other, you see a Hello World example with 30 lines of Python code. And with that, you can train a model which works perfectly, like doing image recognition or speech translation. That's pretty cool. But actually, that's not really the real world, how to bring models to production at scale. Because typically, the data is not really prepared as you get it in these examples, and also it's just running on your laptop in Python and not in an infrastructure to process hundreds of thousands of cars with that. And therefore, you have to really be aware that deploying machine learning to production at scale is much, much more than writing the Python code to train a model. And here you see an example of the hidden technical depth of machine learning. That's a paper written by Google a few years ago. And that shows pretty well that machine learning is much, much more than writing the Python code. That's this small black box, which you probably can't even read in the back of the room. So it's much more really, you have to think about data collection first. If you connect to thousands of cars, that's a lot of data. That's not what 20 lines of Python can solve for you. On the other side, also for model training, that has to run really at scale. You have to ingest all the data into a data store to train a model. And then you have to serve the models so that they can act in real time on all the sensor data from thousands of cars. And then you have to monitor the whole infrastructure on a technical level and also on a business level. So it's really a huge challenge to do that in a real world example. And therefore, the good news is there is a lot of examples in the internet how companies did that before. It's no surprise it's the tech companies which always have these kind of problems. A few years before, the traditional companies have similar problems. Like Netflix has already built a recommendation engine to do recommendations with machine learning to every single user. So every one of us in the room gets specific recommendations on its tablet or on its iPhone or wherever you watch their movies. Uber has built a machine learning platform, Michelangelo, which is framework independent, so you can use anything like TensorFlow or like any other framework, like deep learning for J, H2O, whatever. But they have built a template around that, though, that you really can bring that in a scalable infrastructure, both for the training part and for the deployment part of the models. And the third example is PayPal. So this is an example which often sounds like a more trivial use case because it's just about fraud detection. But even if you want to do things like fraud detection, where the fraud changes all the time, this is not just about training one model, but it's many different models, many different algorithms, and combining them, do A and B testing, and all of that in a reliable way at scale, because if these kind of fraud detection systems do not work at any time, then PayPal is in trouble. And with that, and that's also already the connection to Kafka and what I want to explain in much more detail. Most of these examples where we really have a scalable and reliable infrastructure for machine learning somehow use Kafka under the hood, at least for parts of it, not necessarily for everything. And that's in the end where I now want to connect this, how this works together. So on the one side, we have different machine learning algorithms and frameworks. And on the other side, we want to do that in a scalable and reliable way. And therefore, often Kafka comes into play, which really got the de facto standard more or less for streaming platform, which means it's a highly scalable and highly reliable system to do not just messaging, that's one part of it, but Kafka also stores the data. So you can also decouple different systems from each other very well. And you can even process the data with Kafka. So this is not a deep dive into Kafka, so if you don't know it on a high level, it relates to process data at scale in a reliable way. And one important point to mention is that Kafka, so even the Apache Kafka framework without any additional tools, is not just the core in the middle. That's what many think about Kafka. This is the messaging and storage part. But even Apache Kafka, if you download that from the Apache website, it includes Kafka Connect for integration, and it includes Kafka Streams for stream processing. And that's important to understand because I will also show how you can use that in a machine learning infrastructure. For example, we use Kafka Streams to deploy the models for processing in real time at scale later. So with that Kafka, while it was developed by the tech companies and they used it at extreme scale, there are really 2 points I want to point out here. The first one is, of course, that Kafka is not just used by the tech companies. In the meantime, probably every bigger company has different Kafka projects for different use cases. But even more important, Kafka is not just used for big data projects. And that's a conversation I have with all the customers all the time if there's a new project which thinks about using Kafka or not. And they often say to me, well, we don't have much data, so is Kafka the right thing? And in more and more use cases it is. And the big thing is Kafka can be used for large scale, like the connected car infrastructure. But also it's often more and more used for smaller data sets and sometimes very small data sets. So We see more and more companies building, for example, instant payment applications with Kafka. There it's about 100 or maybe 1,000 messages per second. But the huge benefit is not just the messaging. The huge benefit is the high scalability and reliability. So Kafka is built for failure. Even if a node is down, Kafka is not down. You don't lose any messages. And also, as important, it's decoupling the different systems because it also stores the data. That's very different from a queuing system or any other ETL tool compared to Kafka as central integration layer. So therefore, this is just an overview about different use cases to explain that Kafka is used for many things. And with that now, let's think about how we can use Kafka together with machine learning. And here's an example. Here you see the two parts of machine learning and how it's connected to Kafka. Machine learning, if you're not that experienced with that, it's always two parts. First, you have to ingest a lot of data into a data storage. That's historical data, and then you train your model on top of that. That's the first part, model training. And the second part then is when you have your model, then you can deploy it somewhere. And that's where you do the model inference, the model predictions on new data. And therefore, these are the two parts, and here you see how Kafka is related to that. And often it's not just the Kafka core, which is the thing in the middle, but often it's several other systems from the open Kafka ecosystem which you can use. I will cover this all a little bit in more detail during the talk. But the point really is, and that's solving this impedance mismatch between the data scientist, which wants to use Python code, and on the other side, the production engineer, which has to deploy that stuff to scale for reliable infrastructure and deployments. And in the connected car infrastructure we see in this use case, it's really about highly reliable and highly scalable things. And therefore, you need an infrastructure like Kafka. But still, the data scientist can use it from his perspective to integrate with that, to do the processing and the model training. So back to our use case of our automotive company. And that's also really what we see in the real world very often. This is really step by step. You don't build everything at once, of course. And like at Audi, for example, in Germany, the use case here is that the connected car infrastructure already exists. And however, it exists in this case on AWS. So that's what the decision was for this infrastructure team. So that's their most critical Kafka cluster because they ingest all the data from the cars via some proxies to this Kafka cluster. So that's the most mission critical one. If that's down, everything behind that is down. However then, the big point is here that this is on AWS. And on the other side, our ML team in this case uses Google Cloud as strategic cloud provider. And that's really very common in the real world at the big companies. Typically, we see really hybrid deployments where some stuff is on-prem. I will talk about that later. And also where you use multi-clouds for different things. Different departments make different decisions. It has political reasons. It has technical reasons. Like in this example, Google Cloud is probably the best one for, or most innovative one for ML because they work much on TensorFlow and these things. So they do it very well, also with community and open source and these kind of things. And therefore, in this use case, and that's very, very common, is that we have the one critical Kafka cluster which ingests all the data from the streaming data. And then, while some mission-critical applications run exactly on that Kafka cluster in AWS, you also replicate the data to another Kafka cluster. In this case, it's an analytics Kafka cluster. It's not that critical, because if that analytics cluster is down for an hour, you can survive that, because it's just creating models. And in many use cases, it's OK if it's down for an hour. But if you have the really critical applications, you have them on AWS. But here we replicate the data to another Kafka cluster that's completely separated then, and there we can do our analytics. And maybe we can even try out things which might crash the Kafka cluster, use too many resources, or whatever we do wrong. It's decoupled from the other one, and that's the good thing here. So let's assume now we are the analytics team, and we have set up this replication. We are now on Google Cloud. We get all the data from the different cars, stream it in. This is really terabytes of data. And this can be used to train models. The first thing we have to do before we really can train models on the data, we have to pre-process the data. And that's a big step, especially if you think again about these kind of big data use cases, because that's really also hard to do with just Python code if you want to scale that up and do this in real time or very fast in a reliable and scalable way. And therefore, you can leverage Kafka for that too, because Kafka is not just a messaging layer. Kafka also includes Kafka Streams, which is a stream processing engine. With that, you can continuously process the data at scale. And that's very important. you could also use something else like Spark Streaming or like Flink. Then you have to first ingest it into that other big data cluster and process it there. That's also a valid approach, right? In this case, it's but even easier for this, because all we want to do here is some pre-processing on the streaming data. And so this team doesn't want to use another big data cluster to manage for that. They are even fine with just one cluster to manage. And so they use Kafka native stream processing, either with Kafka Streams or KSQL. The huge advantage here is that you leverage all the Kafka benefits under the hood. High throughput, high availability, all the technical things you know from Kafka, like offsets, consumer groups, replication, that's also built into the streaming engines on top of Kafka. So you have only to manage one scalable Kafka cluster and do all the processing on that. And that's a huge advantage for many use cases. It makes operations and development and testing and monitoring much easier than having two different clusters for doing that. Because most Spark and Flink deployments also have Kafka as ingestion layer, because Kafka is the scalable way to ingest data there. And it all has its trade-offs, but in this case, we do the native Kafka processing. And to show you one example here, how we do an example of pre-processing here, in this case, it's hello world data, right? In the real world, it's more columns and more attributes and more data. But here, we just have the car ID and the event ID and some stuff and the sensor input. And here, we also do a join with another stream, and then we do a filter on a specific car type. So this is just a simple example to show how you could do filtering. And in the same way, you could do enrichments, transformations, aggregations, or even what I do and what I will show later in the live demo, I will deploy an analytic model into such a query. So to do very powerful things. And the big point here is really that this solves also the impedance mismatch between the data scientist, which uses things like the Python language or the Jupyter notebook to do rapid prototyping and to try out things, do pre-processing, anonymization, feature extraction, all of these things. But the big point is this query you see here, this can also be deployed to production afterwards. So this query can be deployed to one or more KSQL servers. And because that's all Kafka under the hood, this scales to hundreds of thousands of messages per second and is totally reliable like any other Kafka application. And this is really huge because it's very simple on the one side and also very powerful on the other side. And that's pretty powerful solution to do this kind of pre-processing. I talked much more about this in my other talk on Monday about this with Jupyter and Python and so on. If you're interested, just check my website and SlideShare and so on. There I have more details about the view of the data scientist on Kafka and KSQL and all these kind of things. But here now, assume we have done this kind of pre-processing, like anonymization of some data. That's important, of course, for driving data for people. And now we want to train our model. To do that, we have to ingest the data into a data storage. And that's also, again, at scale, reliable, where you can also use Kafka, because if you use that as processing layer anyway, you can also leverage Kafka Connect, which, again, is part of the Apache Kafka project. And you can use that to do integration at scale, like Kafka Streams or KSQL for processing. Kafka Connect for integration also uses all the Kafka concepts under the hood, like consumer groups, like offsets, replications. It's all the same like Kafka under the hood. And therefore, you can integrate, like in this case, what we do, because we are on Google, we store all of that into Google Cloud Storage, which is an object store like AWS S3. And then we can train our models on top of that. However, of course, then, you could also store it in different data stores in parallel. This could either be really just big data stores like HDFS also, if you want to use different technologies on that. Or, of course, and that's the beauty of Kafka, while the first use case here might be storage into Google Cloud Storage for model training, any other consumer can, of course, also consume the data. And each consumer is decoupled with Kafka, and therefore, one can be real-time, one can be near real-time, and one can be batch. That's totally fine because they're completely decoupled. That's one of these huge differences from Kafka compared to traditional messaging systems like an MQ or JMS system. So now, let's think about how that works in a little bit more detail. So we need to do this integration, and for that we can use Kafka Connect. And Kafka Connect, it's more or less really just a wrapper on top of Kafka to do native and scalable stream processing with all the benefits under the hood. And it's also scalable. So you can either have just single standalone workers for doing deploying a connector, or you have a scalable Kafka Connect cluster which runs more instances to have higher throughput and parallelism. and also a high availability without data loss, even if a node is down. And so to connect the dots here to how this looks like in a real-world architecture, here's an example now. We get the streaming data from the cars in some way into the Kafka cluster. In this case, we use a proxy for that. You could also use Kafka Connect here, or you can use just the .NET API or whatever from Kafka. And also, we ingest data from a relational database. So it's not necessarily just streaming data in Kafka, right? In this case, it's also a database information, which is you can either pull the data with JDBC to Kafka, or you can do change data capture, so that you push data changes to Kafka. And then you can use things like KSQL or Kafka streams to process the data continuously. And you can even join different streams of data. And then you send it somewhere else. Like in our case, we want to send it to a Google Cloud Storage with Kafka Connect so that we finally can train our model on that. But in parallel, there can be other consumers. Like here you see also a Kafka Streams consumer, which does some other stuff with the data. So finally, we have it in the Google Cloud Storage. And now we can finally, after all this work, train our model. So here again, writing the Python code to train the model, that's just a small part of the task. And that's what the data scientist spends maybe 10% of its time on. It's much more about data analysis, data preprocessing, and these kind of challenges where you have to spend your time to train models. The tutorials you see on the web, that's already the Hello World stuff with prepared data. So that's much easier to do. So now finally we can train our model, and that's also the beauty of cloud, and that's why so many people go to the cloud for machine learning, because here you have elastic scaling, so you can even train big data sets, but you can spin up new instances. You train your model for an hour or maybe for 2 days or whatever your scenario is, and then you shut it down again. And you can also use specific hardware for that. Like in case of Google, they have built TPUs, which is TensorFlow processing units, which are dedicated for deep learning, which does some kind of matrix multiplication, which works much better with them. And therefore, this is great in the cloud. You can really pay as you go with that for model training and scale it up and down without buying own hardware in their own data center. And so finally now we have trained our model. That's great. So in this case, like you normally do it, you store it in a data store like Google Cloud Storage at scale, and from that you do a model training. However, there is even an easier approach today with Kafka, and that's really a huge innovative improvement, which I think was released 3 months ago or so. So in the meantime, you can even do model training without an additional data store. So the very normal way today is to store it in HDFS or in S3 or Google Cloud Storage, and then you train your model on top of that data. Today, what you can also do, you can do streaming ingestion directly from Apache Kafka topics to TensorFlow. And with this, you eliminate the middle storage. And that's huge for some use cases because it's much simpler to operate and much cheaper to do. And under the hood, this is using the TensorFlow IO add-on with a Kafka plugin. So that's part of the TensorFlow project. And with that, you really can stream the data directly from Kafka into the TensorFlow training and don't need another data store with that. That's a pretty cool thing for many use cases. But no matter if you use an additional data store like Google Cloud Storage or you do direct streaming ingestion, finally then you have your analytic model. So we are done with the first part, right? We did ingestion and preprocessing at scale with Kafka. We trained our model with TensorFlow. And now we have a model. So if you're not that experienced with machine learning in general and come more for the development perspective, an analytic model is no magic, right? Even if it does cool things, it's not magic. It's just some kind of code and rules under the hood. So in case of TensorFlow, an analytic model is a protobuf file. In other products or frameworks, it's maybe XML, it's maybe Java, it's maybe some proprietary code if you use something like SAS or whatever. I don't know actually what they use as binary. But it's a binary, and therefore you can ship it to anywhere else. So the good thing is that the model training is completely separated from the model deployment. So even if you already have your infrastructure in place for model training, let's say you just use Spark from HDFS without Kafka or so, still you can deploy the model now to a Kafka real-time application. So this is completely separated things because a model is just some kind of binary, depending on what technology for the ML framework you use. And in our case, as I said, we trained a model here from sensor analytics for anomaly detection. So this is an autoencoder, and I don't want to go into much detail here, but in the end, you get all the data into the model, and then you compress it, and then you try to reconstruct the data. And depending on how big the reconstruction error is with this model, it detects if it is an anomaly or not. Because if you cannot reconstruct the data with a compressed information, then there is too many anomalies. So that's the high-level explanation of how an autoencoder works, and that's what you can use for anomaly detection, like we use it here for predictive maintenance, as I will show you in a few minutes in the demo. So another side note here is, of course, then you can also combine this with fancy things like with AutoML. So that's a new technology or paradigm or different solutions which simply take over most of the parts for you for model training. So in the real world, you don't train just one model, but you train different models with different hyperparameters, with different information, and compare them to each other. And then even often with different frameworks to see which model works best for your use case, which is the most accurate one, to deploy the right one, or with A/B testing different ones. And that's also the beauty of Kafka, because in Kafka, everything is stored in a log, right? It's event-based, stored with timestamps, step by step, and you can consume the data again and again and again. That's the beauty of Kafka, because you can configure a retention time as long as you want. And that's very different from traditional messaging systems. And so, for example, you could train 2 different TensorFlow models with the exactly same data. And then you can compare which one works better for you. And then, maybe at the same time, or maybe half a year later, when a new technology for ML comes out, you can use that technology. Like here you see, first we train 2 TensorFlow models, and maybe half a year later, we want also to use DataRobot, which is an AutoML tool for training models. And then you can compare them and deploy the best one. And you can use do all of that with the same data and the same events. So no matter how you do that, in the end, now we have trained our model. So this was the first part, right? So the automotive company ingests all the data from the car somehow to the cloud and trains the model there with some technologies. That's great. On the other side, a model only helps if you can also deploy it. So otherwise, you don't get any benefit out of that. So you want to add value out of that. And that's also the next big challenge we see at many customers. So I've seen at least 5 customers only this year where the data science teams, which in big companies are completely separated from some other development teams, created great models with Python, which were very accurate to do predictions on fraud or predictive maintenance. And then when it was done, they handed it over to the engineers and said, well, this is great, we can now deploy it and save a lot of money. But there was the problem, because the data scientists only used Python and had a Python model which did not scale, it was not performant, and it did not work the way it needed to work in the real world use case. And therefore the key lesson learned, and what we recommend, is that really these teams work together from the beginning. That's very common in smaller teams or in the tech companies here in Silicon Valley, but in the traditional companies, this is often really one of the biggest problems also. Anyway, so we have now trained this model, and now we want to deploy that to production. The first big challenge here is often model training can happen anywhere, even in the cloud. Of course, you have to anonymize some data and cannot use every private information, but you can even store it somewhere in another country. Like I'm from Germany, and there it's very critical where the data is stored, so you cannot even store it in the US, right? And so, but for then model deployment, when you really want to use the data in real time, like in our connected car infrastructure, we want to send alerts to the driver, please stop your car in the next minute or your engine might break. Or even more customer-related things like what car manufacturers do more and more, they build digital services, for example, for cross-selling. So even car manufacturers in the future have a loyalty system and all these things to know the data of the customer and connect that also with other systems, not just the examples like a weather service to know what the weather is on the street, but also things like with the restaurants. So, and if they know a customer likes McDonald's, then they might send them an alert, hey, here on the Autobahn in Germany, here is the next McDonald's in 10 miles. If you stop there, you get a coupon for $2, right? That's how they connect with other services to make more money and provide digital services. And with that, it's really critical because it's PII data, so it's very private information. And this is a different kind of how you deploy it and where you deploy it. And therefore, the model deployment has to be at the edge, whatever that means, but it cannot deploy in an AWS cloud where the data might go to the US. Right? And therefore, the good thing is model deployment is completely separated from training, so that's all okay. And that's a good thing. So you can do local processing and local predictions. One thing to note here really, and that's also a lesson learned from many customer conversations, really define what you mean with edge, because everybody means something different with that. Here you see there's many things you have to discuss. What do you mean with edge? Does that mean you have an edge data center, like in every region in Germany or in the US? Or does it really mean the edge for you is the car itself? And in the car, you typically don't have some kind of cluster or even broker. There, typically, you have just a smaller client which sends out data, for example, with MQTT to another server. And there is a lot of things you have to discuss here. And then also, even again, with privacy and so on, you have to think about, can I send all the data to a local store to train it together? Or can I only do local training for the specific person in the car and only can send a result back to another server in the back end? So that's the questions you always have to discuss. There is no specific answer. But to show you one extreme example of what some people mean with the edge, and this is an example, here's from Telco, from a solution, but it's the same for manufacturing and automotive and so on. So here, this is one solution which is based on open source, like OpenStack and Ceph for storage, and also it runs Kubernetes. So here you can already see, and if you take a look at the hardware requirements, this is really a big edge thing. So this is more a thing which typically is deployed in a data center. But for them, it's the edge. It's a thing in the edge, and they define edge here at if the latency from the application end to end is less than 100 milliseconds, then that's edge for them here. So always define what you mean with that. And when we know what we mean with edge and want to deploy our model somewhere at the edge, then we have different options. So the option number one is that you deploy your model to a model server. In case of TensorFlow, it's TensorFlow serving. That's a server which you can either use in the cloud. So for example, Google ML engine is hosting that for you. It's then a serverless model server where you can just deploy your models. It has huge advantages like A/B testing, model versioning, automatic monitoring, and all these kind of things. The big trade-off of this approach is, especially if you want to build a real-time system or a scalable, robust system, that you always have to do this RPC call, which you see here. So even if your application is separated, you have to do this RPC call to somewhere else. And many technologies only provided with HTTP, which is even worse. Some at least with gRPC, like TensorFlow serving, that's at least more performant. But still, you have this problem in the middle. If the network does not work well, or if the performance is not good enough, you have latency problems, then you're in trouble with your application. And therefore, the other option is that you natively embed your analytic model into the streaming application. And that's much more robust and much more real-time, because you don't have to do other connections to other systems. It's just a one application. And this can even deploy, for example, offline, right? Because you know all the things you need to know to do the prediction here. Both of these approaches have their trade-offs. It's not that one solution is better than the other. It simply really depends on the use case and the complexity and the experience, what to choose, but you should always be aware of both options. I will cover exactly this topic in 2 weeks at Kafka Summit in San Francisco in much more detail. So after that, the slides and the video recording will also be public, so you can take a look at that in more detail if you're interested. There I will cover more examples. So for example, also how you can deploy a model in a sidecar with Kubernetes and all these different options you have then. So, and the other part then, and that's I think the last part before I come to a live demo, is that the good thing about Kafka in general is that you decouple systems. So you have different producers, like all the cars, and you have different consumers, like the ML engine, and also real-time consumers for alerting, and maybe an Elasticsearch for search engines. They're all decoupled, and that's great. But one thing which often comes in mind then is governance, right? So you have to ensure that all speak the same language regarding a message structure. And so how can you enforce that? And that's typically where in Kafka environments the Schema Registry is used. With the Schema Registry, you can enforce that the clients, both the producers and the consumers, use the right language in terms of what message they use. Like in an Oracle database, you define a customer with an ID as integer, with a name as string, with an email as string, and these kind of things. And that's really huge, and it has a lot of other advantages, like it also has backwards compatibility, so you can even change the schemas over time and still the systems are not down. And therefore, in most new Kafka projects, we see the Schema Registry is used for exactly these reasons. Because typically in Kafka, you don't have just one consumer of data, but you have more consumers. even if you have just one consumer at the beginning, as soon as you provide this interface to other projects and teams, there's many more which want to get this data typically. And the last part about such an infrastructure, and that's also important, is then how to monitor all of that. So on the left side, you see this kind of architecture I discussed. It's both for model training and ingestion and transformation, but then also about model deployment. You have to monitor that, both from an infrastructure perspective. Is everything running well? How's the performance? Do we need to scale up? But also the business monitoring. So how accurate is our model? Should we do A/B testing with new models? I mean, you always have to do new models and deploy them every week or month or whatever your use case is, even more often. And so there's only custom solutions, but most also then somehow build that on Kafka, because if you have Kafka there anyway, it's a scalable real-time system for high message volume, then you can also build monitoring on top of that. But then also, of course, send this information to other systems like Prometheus on Kubernetes or any other tool you use for monitoring then. So with that, that was more or less this kind of story, how to do both model training and model deployment and leverage Kafka for that to build a reliable and scalable system. And now let's take a look at an example, which I also will demo quickly. So here the idea now is we have the car sensors, which send the data via proxy to the Kafka cluster. And what I will show here now is you get it to the Kafka cluster via MQTT, and then you use KSQL to do processing on that. In our case, what I will show, I will really use an analytic model here to do predictions in real time. And then when you have these predictions, then you can use them in different ways. So on the one side, of course, you can use your real-time emergency system. In case of predictive maintenance, you probably will send both a message to the car itself, which is also connected to the internet, so that the car shows in the display, please stop the engine. And on the other side, you also probably send a message to the mobile phone or mobile app the user has done. And on the other side, that's only the critical information. That's probably 0.10% or so of the messages. And on the other side, another Kafka consumer could consume all the predictions, not just the alerts, but all predictions. And for example, use a tool like Elasticsearch to get more insights out of that again. So that's the beauty again of Kafka. Different consumers can do that. And here in this example, the alerting system, of course, has to be in real time, so in milliseconds or seconds. Elasticsearch or even more batch-like tools like Hadoop, that's more like in minutes or even in hours. That doesn't matter because there it's more about reporting or training new models or so. And so this can be totally separated. The real-time system consumes the data in real time, and others consume them when they want. So what I want to show now quickly is here the example. So I create a new KSQL query, which uses a user-defined function. And therefore, I don't want to show just something very simple where you could filter or transform data. But in this case, I really leverage an analytic model under the hood to do these kind of predictions in real time. And that's what I want to show for a few minutes. So what I'm using here, I have all of these examples on GitHub on my website. So in the end here is really, you see exactly what I just showed you on the slide. And you can also try it by yourself. It will try out of the box. And what I already did, I already started my local Kafka environment because it takes 30 seconds or so. So here you see there's a Confluent command line interface, which is open source. You can easily start that with one command. Here we need Zookeeper and Kafka as core, and we also need the KSQL server for doing the processing. And with that, first what I will do, I create a new Kafka topic. So in this case, the Kafka topic is called temperature, and this is simulating the engine temperature from the car. Again, this is hello world. In the real world, you have many different information you have to aggregate and calculate, but it would work the same way. You have just to do more work around that. And now we have a topic temperature. And the only other thing I have to start is my MQTT proxy. So what I do here is, let's take a look at that first. Kafka MQTT quick start. This is the configuration of our proxy. Proxy is a tool where you can directly forward the data from MQTT devices to Kafka. So this is simply another option. You could also use an MQTT broker and send the data from the MQTT broker to Kafka, for example, with Kafka Connect or any other integration. in this case, because what we heard exactly in these use cases like manufacturing or like automotive, that here the MQTT broker is just overhead. They only had it to send the data to Kafka, and therefore it's more cost, more operations, different infrastructures to test. And therefore we also have built an MQTT proxy to directly push the data from the MQTT device to Kafka. And therefore that's what I'm using here. I'm starting that. And so now we have the whole infrastructure running to do that. And let's see, yes, it's running. And so what I'm now also starting is the KSQL command line interface. So as I said before, so this is often things which the data scientist does or data engineer or even more like a BI user. And so this is pretty easy to do. This is where you write just very simple commands and then also SQL commands. But this is directly connected to your Kafka system. You see here some internal Kafka topics and also our temperature Kafka topic. And we could use that from Python, from Jupyter, via REST interface, or I do it here now in the command line. And the other important thing is what I do now here with development. So this is for interactive analysis, for trying things out. The same queries I use here, this exactly same queries could be deployed to production without any code or any other changes and scale to hundreds of thousands of messages per second because it's just Kafka under the hood and the stream processing engine. So here I create a stream sensor, and again it's hello world, it's just an ID and a sensor input. And so this stream sensor listens to the Kafka topic temperature. And I just use one more command here, and in this case I use a select query where I select the input, and I use the user-defined function I defined before to detect anomalies on that data. And this under the hood uses the TensorFlow model in real time. You don't have to understand that or care about how that works as end user. This is what a data scientist or an engineer implements once, and then you can use this as end user. And so here now, this is running continuously. We talk about stream processing. It continuously processes data if you would deploy that to production. And so here we are waiting now for input data. And so what I can now do, I use the Mosquito pub client. This is an MQTT client which sends the MQTT data. And the important thing here again, as we use an MQTT proxy, I don't even have a MQTT broker running in the middle. I just send MQTT data. Here you see to the car/engine/temperature topic, MQTT topic, and the MQTT proxy forwards and pushes that into Kafka. So now you see this is the sensor data, and as soon as I push return on my laptop, the proxy on top forwards the data to the KSQL query and does the prediction. So the left is the ID, so here it's just one sensor, and it's sending information. This is the result of the analytic model. And so we could also use a sensor generator, which I have here. So this is now generating random data, and so it's always giving a different prediction. And based on this now, if you think back to the use case, you could define a use case like if you have within 10 seconds like different values, and if 3 of the values are over 4 or whatever your threshold is, then this is an alert or at least a potential defect, and therefore we will send an alert to the driver that the engine might break. So this is really hello world here, but this is how it would work in the real world too, with of course other data sets and so on. So this is how this looks like. It's pretty easy. And also to show you this user-defined function, this is really just a little bit of code to write once here. In this case, I just use the UDF API from KSQL, and I use the API from the analytic model. In this example here, it's H2O. It's not TensorFlow, but it's exactly the same. You use just a specific API of the machine learning framework. And with this, you can use that. Here you get your input data, and then you do some data mappings here to have the right format. And then you do your prediction here. So this is the magic line, which in real time, for every single event of the hundreds of thousands events, does the prediction in real time and sends the output with the return here to a Kafka topic. And from there, this alert can be consumed either in real time or in batch by any other system. And that's how this works. And actually, we are also building a pretty cool other example these days, so this will probably take 4 to 6 more weeks. But what I just showed you was the Hello World example, and what we will build in the next weeks is really an example where this is shown at scale. Because the interesting thing is not when you do this hello world on your laptop, but when you scale this. And we will show a demo on Google Cloud where we have really 100,000 connections, devices, which produce data all the time. It's very similar to what I just showed, but not as hello world, but with real sensor data at scale. And still you can do that in a reliable way at real time. And so you can just come back here in 6 weeks or so, and I will probably also do a talk about that soon. And with that, I'm done with the demo and also more or less with the talk. So let's just go to the final page. So this hopefully was a good overview to connect the dots between machine learning and between Kafka and how you can leverage both together to build scalable and robust systems. That's what we see really also more and more in use cases at our customers, and very important also, really model training and model deployment are separated. So it might even just help for one of these two use cases. And with that, the time is also already over, so if you have any questions, please come to me to the front, and I hope this helped a little bit, and thanks for coming.